familiar with apps below, like Didi and Uber. Their success is owing to the rapid progress in mobile internet and sharing economy, as well as the urgent demand of sustainable transportation system, as ride sharing can effectively relieve the traffic congestion and air pollution problems. And with the help of big data, we have more chances to design some new algorithms to improve their efficiency. And we know that there are many types of ride-sharing applications, but the core issue remains the same. That is order dispatching problem. And we can see below, there are 3 typical roles in ride-sharing. First, the passengers can submit requests to a platform like Didi, and then the platform will assign orders with suitable drivers. And this progress is also called order dispatching. And after that, if the order is not canceled, then the matched drivers will serve the orders. And there can be many objectives of this problem, like minimizing the total waiting time of the passengers, but the most concerned objective of the platform is to maximize the total profits or the total revenue. And so how can we model this problem? We can see the example below. There are 3 passengers and 3 drivers. And serving each passenger will give the driver or give the platform a reward. And the platform wants to maximize the total revenue. A natural idea to model this problem is using the bipartite graph here. The nodes from the left and the right side can represent the passengers and the drivers, and the edge between the nodes can represent the rewards of them. And the problem will be converted to maximal weighted bipartite graph matching. And this problem is very classical. Early in the 1950s, Dr. Harold Kuhn solved this problem by the famous Hungarian method. And he also told us that the optimal solution can be found in polynomial time. But our problem is much more difficult because the real scenario is dynamic. And as we can see from this example, actually the drivers and the passengers will appear sequentially to the platform, and we cannot forecast their positions in advance. So this makes the problem two-sided online bipartite graph matching. And the one-sided online bipartite graph matching was first studied in the 1990s by KAP, and the two-sided case is much more difficult. Even recently, some recent work also studied the two-sided bipartite graph matching theoretically, and some new progress has been made recently. And so the dynamic scenarios makes this problem very hard, and it is almost impossible to calculate an optimal result in an online scenario. And existing methods, they are also called the online algorithms. They aim to find approximated results, approximated solutions, and they have derived strong theoretical guarantees, but they are also based on strong assumptions like the instantaneous constraint. The instantaneous constraint here means we should match the nodes as soon as their arrivals. For example, here, if 2 drivers have arrived, and the passenger P1 has arrived, and according to the instantaneous constraint, we have to match P1 immediately. So we use a greedy choice here, and we match P1 to driver D2. And however, sometime later, a new passenger P2 has arrived, and he has a higher reward with D2. But D2 has already been matched, so in this case, P2 cannot be served. And we think the instantaneous constraint is too strong sometimes, and also impractical. And we hope if the nodes can wait, maybe some better candidates can be met in the future. And this idea also develops into the batch-based solutions. We can see in this same example, with a batch, and we accumulate the four nodes into this batch, and we match them together, we can get a reward of 6, and both P1 and P2 can be served. And the batch-based solutions have gained much popularity recently, and many real industrial solutions like the matching algorithm in DD are also batch-based. But most of them are based on fixed batch sizes. We can see from this same example, if we use a fixed batch size to the batch size fixed to 2 seconds, then we find that the matching result is not good enough because the highest reward between P2 and D2, the highest reward is not get. So the fixed batch-based method can be too rigid sometimes, and they cannot adapt to the strong dynamics in supply and demand. So our target here is to design adaptive batch-based methods. Actually, there are 2 different types. The first is adaptive batch size selecting. It means we use adaptive batch size here, but in each batch, we still use fixed in-batch decisions. And another is adaptive in-batch matching. It's just the opposite case. That is fixed batch size with adaptive in-batch matching algorithms. So how can we make the solutions adaptive? We finally come to our major topic today, that is by using the reinforcement learning techniques. And next, I will talk about the two corresponding reinforcement learning solutions. First, I will talk about the adaptive batch size selection. Apparently, it is different from our traditional online algorithms, and we use a new representation here. For each possible batch splitting strategy, we use a binary vector here. And for the boundaries, we use 1, and otherwise we use 0. And we also restrict that each in-batch algorithm should be the Hungarian method. For example, KM algorithm as an implementation. And so with a batch splitting strategy, we can precisely get the matching results on online graph. And before we discuss about how to compute a good strategy, let's think about another question, that is, why should we use a Hungarian method? Why not other algorithms? Because in an online setting, a local optimum does not always lead to a global optimum. And to answer this question, I think we need some further analysis. So we use the competitive ratio as an evaluation metric. It is defined as a ratio of the online algorithm results and the offline optimal results over all possible graphs. And it can reflect the worst case performance of an online algorithm. And we have the following conclusions. Due to time limits, I will just skip the proof here. And the first conclusion, if we remove the unmatched nodes in each batch, and then with KM as an in-batch algorithm, there will exist a strategy that can achieve constant, also tight competitive ratio of 1 over C minus 1. Here, C is a constant. And the second case, if we keep the unmatched nodes in each batch, then the competitive ratio is still a constant and even better, but not so tight. And more details can be found in our paper. And so we have proved that using the KM as an in-batch algorithm, the adaptive batch-based method can have a global theoretical guarantee. But this guarantee is conditional. It is for the best possible strategy, but how can we find the best strategy? So reinforcement learning has come into our site. This batch selection problem is exactly a sequential decision-making problem, and naturally we can model it by an MDP. And here is how we model this problem. The state, it can be the graphs in each batch, and for simplification, we can use the number of nodes on the left and on the right. And the actions are 0 and 1. And the reward is 0 if the action is 0, and the reward is the sum of the weights of the matching results if the action is 1. And the transition is the distribution of the newly come or left nodes. And the nodes will leave if we match them or if their deadlines have come. And to find an optimal batch splitting strategy, then will be equivalent to finding optimal policy in this problem. As we all know, under specific assumptions, the classical Q-learning algorithm can converge to the optimal policy. And so we design a very simple algorithm based on the standard Q-learning. And here is a running example with learned tabular Q values. Here is a learned Q table, and the first node comes, and the number 6 beside it is its duration. And we first check the table, and we find that the state is 0, 1. It means there is 0 node on the left and 1 node on the right. So we will take the action greedily according to the Q values, and we take action A equals 0. And then it means we do not split the batch here, and we repeat this progress until we find some place to split the batch with A equals 1. And then we will get a batch with size 4 and reward of 6. And we will repeat this process until we find the second batch with a batch size of 2. And the values in this table can be updated according to the Bellman backup. And we also find that when the nodes are coming densely, the batch sizes will be larger, and when the nodes are sparse, the sizes will be smaller. So the batch size can be selected adaptively according to the nodes distribution. Actually, we have also proposed an improved algorithm. We assume the batch sizes have upper and lower bound, and but the basic idea is still based on Q-learning, and so I will omit it due to time limits. We have conducted some experiments on synthetic data, and we can see that the adaptive batch-based algorithms can easily outperform the fixed batch-based methods, and they are also efficient in running time and memory. We also vary the graph sparsity and the arriving density of the nodes, and can achieve similar results. We have also conducted experiments on real data from DD's Gaia's program, exactly the same in KDD Cup. And but the difference is that we use a very simple simulator here. We assume that after a driver has finished an order, he or she will immediately become a new driver at the order's destination. And more details can be found in our ICD 19 paper. However, the method above has some limitations. It works for generic bipartite graphs, and although our experiments are based on ride-sharing applications, we do not use any spatial information in our solution, and the learning algorithm can only capture the temporal dependencies. Next, I will present our KDD Cup Winner solution, which uses adaptive in-batch matching algorithm with spatial dependencies. First, allow me to review the problem in KDD Cup. Here, the environment consists of the historical orders and simulated drivers. the driver simulator is built by DD, and we do not have access to them. And the virtual platform will collect the data from orders and drivers for every 2 seconds. And it will form an online bipartite graph with a time window with fixed batch size of 2 seconds. And in the graph, in each 2 seconds will be sent to the agent. Then the agent will decide the matching results and then send it back to the platform. And this circle will run for each 2 seconds. And the platform will send pickup commands to the environment. Then the drivers can carry out the pickup and delivery actions. We should also notice that the orders have cancel probabilities, and also the unmatched nodes will be removed on the platform. And the objective is to maximize the mean total driver income, which is also equivalent to maximizing the total revenue or total profits of the platform, I think. And the problem restricts our solution to be a typical fixed batch-based method. And we have tried some deterministic, also myopic methods like greedy and KM. It means we use a greedy or KM algorithm in each batch. And here, the red bar best, it stands for our winner solution, the performance of our winner solution. And you can see that the myopic methods their performance are not so good. And so we need some more adaptive in-batch matching algorithm to improve the performance. Our main idea is very simple, is to adaptively balance the demand and supply of the system. And here we can have the following observations. First, the demand distribution has some patterns. Here the hot areas and the cold areas can show some repeated spatial temporal patterns. For example, at 9 a.m. on Monday morning, I think the residential areas can be a hot area. And we can predict such patterns with historical data. And for the supply distribution, it is similar, but maybe more dynamic and more complicated. For example, there are 6 passengers on the platform, and 3 of them wants to go left, and 3 of them wants to go right. And we assume there are only 3 taxis on the platform. And if we make the decisions, if we match the taxis to the passengers on the left, then afterwards the taxis will go to the left area, and sometime later, the left area will become a hot area, while the right area will become a cold area. As the number of drivers is assumed to be fixed and also much smaller than the number of orders, so we can estimate the supply distribution in an online manner according to our matching decisions. For example, if our matching algorithm has matched 3 drivers and from area 1 to area 2, then the supply of area 1 will just -3, and the supply of area 2 will +3. And according to the observations above, we can first design a very simple heuristic solution. Here we split the map with hexagon grids, and we can get a demand table. The values are static and can be predicted by historical order data. And the supply are dynamically maintained and can be estimated by the online matching decisions. And we use a ratio of them. It means demand over supply with some normalizations to represent the value of a grid. Then if V is large, we can see that it means the grid is in short supply and maybe more drivers should go there. And otherwise, if V is small, maybe no drivers should go there because the grid is oversupplied. And with the values above, the matching algorithm will go as follow. For a candidate driver order pair with reward R, we will calculate the value of driver's position pair grade 1 and the value of the order's destination grade 2. And we will calculate a new edge weight between them. It is R plus a discounted V2 minus V1. So it means if the destination of the order is more promising than the position of the driver, then the reward will increase. Here, more promising, it means the grid has a higher chance to take more orders. A taxi has higher chance to take more orders in this grid. And so we use, afterwards, we use a KM algorithm in each batch to match all the nodes. And so we find that this heuristic solution is very competitive, actually, and it can be very close to our final winner solution if we do not tune the hyperparameters. But the limitation is also obvious because we use historical data to predict the demand. So the demand has too large errors. So we try to make it more adaptive, and like we can take the values as black boxes and predict them with TD learning. So our reinforcement learning based prediction is even simpler. We use TD0, that is a one-step look ahead to predict the values. And the idea is also inspired by two KDD papers from DD, and the difference is that we use online learning instead of offline learning. And this is our formulation of TD error. And here P stands for the cancel probability, and we use a very simple exponential function to represent it. And gamma is a discount factor, and the T is a discretized duration by 10 minutes. V prime and V are values of the order's destination and the driver's position, respectively. And we initialize the values with the all zero vector, and we have surprisingly found that it can outperform the pre-trained values easily. And the update of the values as follow. And honestly speaking, I think this is not quite a standard IO algorithm, as we take the actions according to the KM algorithm instead of a greedy algorithm. And actually, I think the real greedy algorithm does not exist in this case because the bipartite graph matching has a capacity constraint. It means each node must only be matched once. So I think the real greedy decision does not exist in this case, but it still shows very good performance in the competition. And to better illustrate our method, I will also show a running example here. And in the example, we have three drivers and 2 orders, and it will form a bipartite graph as follow. And we assume the drivers cannot take the orders too far away. So driver D3, it has no edges between the orders. And we assume the initial values are 0. And we also assume the cancel probability is 0 and the discount factor is 1 for simplification. And the reward of the 2 orders are 4 and 5 respectively. So we need to first calculate each new edge weight between the orders and drivers. For O1 and D1, it is the reward R1 plus the destination of the order, the value of the destination of the order, and minus the value of the position of the driver. As the values are all 0, it equals R1 and it is 4. And similarly, we can calculate the values of the between O1 and D2, also O2 and D1. They are all the rewards of the orders because the values are all 0 now. And then we will use the KM algorithm, and we match all the nodes here, and we get the matching results of the first batch. And then we have to update the table. And for driver D1, D2, their position, the value of their position, the grade number 11, grade number 1 will be updated. And as the driver D2, he has taken an order with a higher reward. So the value of grade 1 will be higher, it's 0.5, while for grade 11, it's 0.4. And for driver D3, it does not take any orders, so the value will remain 0. And then comes the second batch. In the second batch, there are 2 orders and 1 driver. And the 2 orders has the same position and the same reward, but with different destination. And we find that for order 3, its destination is grade number 1, where some taxis has taken orders here before, and so the value is not 0, it's 0.5, while the destination of order 4 is the value is 0 because no taxis has taken orders before. So accordingly, the calculated weights between O3 and D3 will be higher, and between O4 and D3 will be lower. So by using the KM, our algorithm will match O3 to D3. And so it also explains that the orders with destinations in hot areas, that is O3, are preferable to our algorithm. And it also explains how our reinforcement learning algorithm runs. And so we finally get the first place in the IO track, and this is team members. And at last, we will see some future challenges. I think the first challenge is how to combine dynamic pricing and dispatching together. In real scenarios, I think dynamic pricing strategy is another way to balance the supply and the demand. Although most existing platforms still use static pricing strategies. And some existing papers already combine dynamic pricing with dispatching for the same maximization objectives, but they use different solutions like the multi-armed bandy for dynamic pricing and TD learning for dispatching. And we hope some future work can use a unified reinforcement learning framework to model this problem. The second challenge, I think, is how to build a good simulator. In the KDD Cup, we have also built a simple simulator to tune our hyperparameters. And we found that the simulator designing is very important, but also very difficult, as many model-based ARL methods can suffer from the distribution shift problem and can cause large generalization errors. And I believe Fanyou will share with us more about the simulator design in the next talk. Then another challenge is not about reinforcement learning, it's a fairness problem. And as we can see, if we have 2 passengers and if the first passenger wants to go to downtown and the second passenger wants to go to the suburb, if we only have 1 taxi here, our algorithm will match it to the first passenger without doubt for higher profits. And however, such a decision is clearly unfair or even discriminatory. And the fairness problem can also happen in the driver side. And I think how to make a balance between the fairness and the profits is still an open question. And that's all of my talk. And thank you for listening.
Thank you, Yansheng, for sharing your work and research in order dispatching. So as I mentioned, we'll have the Q&A at the end. So let's have Fanyou Wu to talk about their research in vehicle repositioning. Let's welcome Fanyou.
Okay, can you hear me?
Yes.
Okay, I will start to share my screen. Can you see the screen?
Yes.
Yep.
Okay, thank you. So hello everyone, I'm Fanyou from the Purdue University. Currently, I am a PhD candidate now. So today I will try to share some of my experience about some machine learning computation and of course the KDD Cup ARL track solutions. So by the way, after listening the presentation from the Yansheng, I think our solution to the KDD Cup is very similar. In one word, we are not only consider the rewards of the orders, but also we take into the destination as a factor to affect the rewards. So today I will use first 5 to 10 minutes to share some of my experience about machine learning computations, mainly focus on the transportation research. And later I will play the video that we submit to the KDD Cup. It will the duration is about 8 minutes, and then I will present some ongoing works that we decide to publish into a journal. And later I will leave 5 to 10 minutes for you to ask questions. So I'm starting to introduce some of my works regarding to structured data computation. In KDD Cup 2019, we attend the regular machine learning computation tracks, and finally we ranked the first for it. The name of the computation is called the context-aware multimodal transportation computation. In fact, it's a very classic multi-classification transportation. Given OD pair and some other information, you need to recommend the best transport mode for it. There are around 1,700 teams attend this competition last year, and this competition is highly competitive. So probably for the beginner who want to participate some data mining computation, those kind of structured data or tabular data computation are preferred, since you don't have any other barriers behind it. You don't need to have much computational results. And later I will show some unstructured data computation that we attend. It's about NIF 2020, the traffic cast computation. It is a standard semantic segmentation task. This kind of task computation is on the other side. There are not many people attend it. So if you have some, you have some access to some of the computing results, then I prefer you should attend this kind of computations. Right now we are still ranked the first, so I'm welcome you can attend this computation as well. And later, let's go into the main topics of today. Some of my experience about reinforcement learning computation. I started my reinforcement learning computation in 2019. When there is the first ARL computation for the KDD Cup. In this computation, there are not many people attend it. There are only maybe 32 teams. Actually, I think the active teams for it is just 10. In the public leaderboard, we perform very well and maybe rank top 10 around them. But later, when the private leaderboard comes, our solution becomes very bad. In this competition, it is a multi-unbounded problem. So there are 2 parameters you can control. The major difficult for it is that we just have a limited training episode. I think for our reinforcement learning computation, this limited episode makes the competition very hard. So, and also makes the leaderboard very unstable. So you can check the leaderboard private leaderboard results. In the end, we just go into the bottom 10. And the interesting thing is that the 29th, there is a team called NTT Docomo. Yes, it's a Japanese team. This year, they also attend the KDD Cup ARL track and finally got third in the repositioning task. So I think, so I conject that our solution to the KDD Cup 2019 and 2020 are very similar. So our strategy towards this kind of computation is to fit our solutions to the public leaderboard. Maybe, so if our strategy will become not very good if there's a huge difference between the private environment and the public environment. So in summary, my experience towards this kind of three type of data mining computations are listed here. Kindly speaking, the deep learning has become much more popular right now. So the unstructured data computation become there are gonna be more deep learning methods comes, and for the reinforcement learning area, it's still not that much computation there. So, but I think the numbers of the computation start to increase. And I checked some of the leading platform like the AI cloud. This year, I think there should be 5 to 10 reinforcement learning computations there. But however, most of the computations have less price. So I hope that many people will try to sponsor this kind of computations. So next session, I will start to share some of my the solution to the KDD Cup 2020. I think the best way to show it is to present the video that we submit to the KDD Cup, not to speak something, because we also provide the good caption from it. Okay, let's start.
University or Southeast University. Figure 1 is the group photo of the main contributors for the KDD Cup. The left one is Yang, and the right one is Fanyou. We own tremendous experience in machine learning competitions, and have owned several top places in those competitions, for example in KDD Cup 2019, IKITE 2019, and Nero IPS 2019. Also, we are familiar with transportation research and publish lots of papers in top transportation journals, for example, IEEE EDITS. However, it is our first time to extend our works to the reinforcement learning area. So we are delighted with this result that we finally received first place in the repositioning track. Our tasks are to involve a combination of order dispatching and vehicle repositioning on and mod platform. Our team focuses on the repositioning task, since we consider it as much easy to formulate it as a reinforcement learning problem. However, we have to point out that order dispatching and vehicle repositioning are coupled in the KDD Cup, which means a good vehicle repositioning agent will also involve carefully designed order dispatching policy. We desire not only succeeding in KDD Cup, but also publishing some papers related to this task. So we restricted ourselves using ARL techniques, especially the deep reinforcement learning frameworks. Now new challenges come that there is no official simulator provided, and some descriptions in environment dynamics are not clear enough. For example, we conjecture each driver may have an attribute of an online or offline state. If drivers are offline, they will not be dispatched any orders. This attribute will generally affect the global distribution of available vehicles, and consequently affect the decision made by repositioning and dispatch agents. There are other hyperparameters that are hidden or simply described, for example, the number of vehicles, so it is difficult to build a simulator, which is exactly in line with the official one. We also realize that there are many ways to formulate this task as a reinforcement learning problem, and currently, there is no common agreement. Which methods and options are better, single agent or multi-agent? Rewards are bounded to grid items or the vehicle, global or local action space, and so on. Those options make this problem open and interested as a research topic, but also makes the competition harder. In summary, to reach first place, we have done some works focusing on, first modifying the reinforcement learning problem statement based on Lin's work, second building our own simulator using Julia language, Third, developing visualization tool to support reinforcement learning training. And finally, applying double deep Q learning to solve the problem. In the following section, we are supposed you are familiar with reinforcement learning and Lin's research about repositioning. We have also put the reference at the end of the video. Problem formulation or statement is the core of the reinforcement learning problem. We generally follow Lin's work and slightly modify it. We simply treat the repositioning task as a single agent ARL task. First, we maintain a global repositioning agent for all vehicles. This setup is straightforward to implement. A vehicle is eligible for repositioning if and only if meet specific requirements. For example, being idle for over 5 minutes. Suppose each vehicle requests for repositioning every half an hour. And there will be 48 samples in a day. Therefore, we design a single agent queue for dispatching multiple vehicles. And the number of samples will be 480, when given 10 vehicles. Here, the single agent works as a global dispatcher, which receives the repositioning requests from the vehicle. It should be noted that concurrent repositioning requests do not exist in the environment of this competition. However, in real applications, the single agent can return an action list, such as the actions that can be matched with concurrent repositioning. And we define the state as the set of global and local information. Global information refers to smoothed vehicle distribution, rides request distribution, and et.al. Local information relates to the time and location of the requested vehicle. Because we use a single reinforcement learning setup, the local vehicle information is treated as an auxiliary input to the model. This one is different from the multi-reinforcement learning setup, which trains different models based on the locations. Note that, since the dispatch window was only 2 seconds, we introduced a smoothing operation, and recorded the sum of the last 10 minutes of data, in each channel, to mitigate the sparsity of the data. We also use global action space instead of local action space. Local action space, like the 6 ejected area related to the current area, is bounded to the place of the vehicle, while the global one can be predefined. We select M number of areas as the action space. In other words, the vehicle can only be sent to a small set of selected regions. Those regions are selected mainly based on net demands. For the final solution, we choose 140 areas. Since the vehicle speed is set at 3 meters per second for repositioning along with spherical distance, directly sending vehicles to the hot zone is preferred. Also, we consider that the online environment for the development phase falls into an order surplus situation. So dropping some order from into the cold zone will enhance stability for the repositioning scores, but lose some incomes. We define the reward function straightforwardly by using the given reward information. To fine-tune the performance of our solution, we apply a reward reshape and add punishment to those orders that have larger pickup time. In the next section, we will discuss some details and implementation of our solution. Table 1 lists some critical hyperparameters for our final solution. We restricted the repositioned vehicles moving within a sub-area, in order to simplify the training process. Other hyperparameters will be discussed in the following. Since the host did not provide any offline simulator, we write ours. Our simulator is written in Julia programming language and is 10 times faster than our Python simulator. To check the performance of a trained agent, we also develop a training visualization tool shown in Figure 2. The web-based visualization helps a lot to debug and fast iteration of our methods. It is critical to make our offline simulator in line with the official one. So we adjust the parameters, for example, the number of vehicles, oversampling ratio, and vehicle and service distribution, to make the GMV curve similar to that of online 1. Figure 3 shows our efforts. We fine-tune some parameters, and finally get a similar GMV curve from the online submission log. Although we are allowed to deploy both dispatching and repositioning agent, a greedy policy is adopted to dispatch orders and drivers for simplicity. In general, at each time window, we sort all order driver pairs by reward per unit time in descending order, and the larger order driver pair are more likely to be selected. Also, we take the order destination as a restricted factor. In other words, when the destination is undesirable, some orders will be declined even if there are available drivers for this order. It takes more than 2 weeks to develop our simulator. When the simulator is set down, applying mature reinforcement learning frameworks becomes easy. We apply double deep Q learning and train it by simple epsilon greedy methods. Figure 4 is our simple network architecture, which composed of convolution layers and fully connected layers. We point out that other advanced frameworks, for example, AEC, might better. But double DQL is enough to reach the top place. One trick for our implementation is that we normalize the input to 0 and 1, since we did not know the real inputs. Thanks for your patience in listening to our shares.
Okay, that's the end of the video. So in general, we provide actually most of our efforts focus on building the simulator instead of starting much about the ARL algorithm. And so since we put a lot of efforts into simulator, we still use it to publish better papers. So this is actually an ongoing work. So now my teammates Liu Yang has taken charge of it and now writing the papers. So the figure 5 and figure 6 are the two graphs I just copy paste from their paper. So in general, we compare 4 methods based on our simulator. It can mainly show that our methods, like the approved global action space, perform better when the request is large. It also meet our experience in the KDD Cup. So thanks for your patience. Finally, I need to take many thanks to Dr. Liu Zhiyuan, his support to our computation. And here is our email. If you have any questions, so please let me know. That's the end of my presentation. Thanks.